We're going to look at the crystal filter today. First, we need to measure the frequency of the crystals we have to see if we can match up a pair. Some books say we want to have them matched within about 20 hertz of each other. There's a couple different ways we can do it. We're going to do it this way, and what I've done before earlier in the week was I took and plugged them in one at a time into the BFO oscillator, and measured their frequency that way. So I've characterized them using the BFO oscillator that's on the bitx board, and now we're going to try this setup here. You see he's using real short leads. Well, why do we want to use real short leads? We want to use real short leads because we don't want the extra added capacitance in the circuit that long test leads would give us. You say, well, test leads aren't any big deal. Well, let's take a look, and we're going to show you just how big a deal test leads are. This is just a typical BNC to alligator clip lead. It's about 3-4 feet long that you might typically connect to your generator to use to do this with. Let's measure its capacitance. Okay, I've hooked my meter up, and hopefully you can read that. It says there's 87.89 picofarads of capacitance there. That's a lot of extra capacitance to throw in any kind of resonant circuit. So what we're going to do, we're going to use a special hookup in order to try to minimize that capacitance. This is our test adapter board. We'll hook up to it with the capacitance meter, and we'll measure the capacitance of it. First, we're going to zero out the meter so we can get rid of the ambient capacitance there. Now it's zeroed within less than a picofarad, so I'll hook the other lead up. And it looks like we've got about 11, almost 12 picofarads. So that's a whole lot better than the 90 we had before. So we're going to use this adapter to connect up and test the crystals. We're going to just plug the crystals into the socket down here, hook one end to the scope, hook the other end to the generator, and when the crystal's in its series resonant mode, it'll have a low impedance, so it will decrease the amplitude of the display on the oscilloscope. So all we have to do is adjust the oscillator frequency until we get a decrease in amplitude, the minimum amount we can display it on the scope, and that will be the series resonant frequency of the crystal. Let's hook it up to the real equipment and try it out. I tested 40 crystals the other day, and using just the oscillator and the bitx board for the BFO oscillator, and I've characterized them here, and I've put them in an access database and I've sorted them. So what I'm going to do, I don't want to test all 40 again. I'm going to just take 4 that looked good using the BFO oscillator, and I'm going to test them with this method and see if the difference in frequency is approximately the same. I'm going to test these 4. These are the numbers that are marked on the crystals themselves, and these are the frequencies that difference, and I only had 13 hertz difference between 4 crystals. So we'll see if that same difference measures out. When I tested each one, I simply took a little sticky tag, put it on it, and numbered it, and wrote the frequency down on a tablet. So we'll start off with number 39 here. It says, and these frequencies will be quite a bit different simply because the coil in the BFO oscillator hasn't been trimmed right yet. So these were quite a bit of difference in frequency. So we're going to just write down the last few numbers just like we did here. Okay, I'm going to start changing the frequency, and remember the object is to get a minimum display on the scope screen. It's going down, so we're going in the right direction. Well, let me trigger it a little better. There's something to be said about using an external trigger, so we'll go on down. I'm changing the frequency at 100 kilohertz increments right now, and it's between two of those, so I'm going to go a step over to 10 hertz increments, and once again we're just going to tweak for minimum amplitude. We're getting awful close there. We can increase the sensitivity of the oscilloscope so we can see it a little better, and I'll go down to 1 hertz increments. And I'm not seeing a whole lot of change here, so what I read is 9.995700. These are 10 megahertz crystals, but they all seem to be measuring down in that frequency, so I'm going to write that down on my chart. And I just need to write down the 5700. Okay, now let's try a different crystal. We'll try another one that was in that same batch, so they should be fairly close. Boy, that looks like it's a lot bigger, so let's change in 10 hertz increments. That says 820. Wasn't very close. And that was crystal number 18. I want to try a couple more just to see if this is going to be the case. Number 33 was right in that same grouping. Big difference. That's 690, that's a little better. The other one was 700. Try one more here. That looks like 650. I'm going to go ahead and run a bunch more through to see if I can find some that match up this way. We're going to inject a signal into our filter, but since our filter is sensitive to capacitance, capacitance actually determines a lot of the bandwidth characteristics. What we want to do is we can't just hook our test lead in here, because we saw earlier where our test lead had about 90 picofarads of capacitance. So what we're going to do is we're going to go back to a stage further in front here. We'll put our input here, and that way the filter sees this normal impedance on the input side. And on the output side, we're going to go ahead and take our output off over here. That way the filter sees its normal output impedance. And we'll sweep through the frequency and we'll see just exactly what the filter response looks like. We're looking at the output of the filter section now. This side of the screen is 9.9 megahertz, or 10 kilohertz below 10 megahertz. And this is going to be 10 megahertz here. Each division is pretty close to being equal to 1 kilohertz. So this says this peak right here on our filter, this would be 9.995, 9.996. So it's just a little above 5 kilohertz below 10 megahertz. The width is okay because we're looking at it's a little over 2, probably 3 dB points would be about 2.5 kilohertz wide. But what bothers me is this big dip. I'd prefer that didn't have that dip there. We're going to see if we can make some changes and correct the dip. Whenever you build something, It's always easy when things don't work out quite the way you think to start to re-engineer the circuit. Of course, you couldn't do anything wrong. The engineer couldn't have possibly known what he was doing when he designed it. My filter's not working right, so I was looking at the components around this circuitry on both sides just to make sure that things were the way they were supposed to be. I run across this 100K resistor. I found I have a wrong resistor at this point right here. I have a 100K instead of a 1K. What that's going to do is vastly change the base bias on this transistor and change the way the transmit side is working into the filter. So we'll go ahead and change that and put a 1K in there, and I'll change it on the drawings and on the component placement on the internet also. And we'll see if that makes a difference in our filter. I've changed the resistor and it doesn't seem to have made much difference, so I'll continue looking for some other problem. Right now I have the unit working up through the filter network. It's not quite right, but it is functional. I thought I'd show a little bit of what it looks like. There's still got some problems and I'm not sure quite what the problem is, but maybe somebody will see this and give me a hand here. Right now we see the carrier is displayed right here. I'm modulating with 2 kilohertz signal. This is the upper sideband. The spectrum analyzer is set up for 2 kilohertz per division, or 1 kilohertz display per division. So we have the carrier here. We'll send it right on. Carrier, and then this is 1 kilohertz, this is 2 kilohertz. So here's our upper sideband. This is the lower sideband. Right now, where this is 10, 20, 30, the carrier is suppressed about 35 dB below the upper sideband. So what I'm going to do is increase the modulation frequency, and what's going to happen is you'll see the amplitude of the upper sideband start to decrease. That's when I hit the upper skirt of my filter, IF filter. It should drop off fairly fast as it goes up. Probably right now I've got the BFO frequency is set just a little bit too high. So what that does is allow this upper skirt to be a little bit too high in frequency. So I'm going to increase the frequency. I'm at 2K, 2.1K, 2.2, 3, 4, 5, and you see I'm 2.5 divisions over. 2.6, 2.7, 2.8. See, now it's dropping off. It's rolling off because the upper sideband's falling down the upper slope of the IF filter. So that's 3.3K. So that's higher. If I go back to where it's up to, it's about 2.7K, which that's probably not too bad. This is the peak of the filter right there, about 2.4K. So if we go the other direction now, they'll get closer together. I'm going to go down in frequency. There's 2K modulation frequency. Now what we have coming up here is the second harmonic of the upper sideband frequency. So when you put a mixer, you get what you get out of the mixer is that the original frequencies, which in this case with our balance modulator, the carrier is attenuated. You get the sum of those frequencies and the difference of all those frequencies and harmonics of them. So this would be a harmonic of the modulation frequency mixing with the mixer and the mixer. The filter should knock that out. Well, it's still down, it's pretty low at this point. It's still down 10, 20, 30, 40, 50 dB down. But as I decrease the modulation frequency, it will come more into the passband of the filter and be attenuated less. So here's 1500 hertz. See how I'm starting to drop off Well, I'm not starting to drop off yet, but I will shortly. I still haven't hit the lower skirt of the filter because this hasn't started dropping down. When the upper sideband starts dropping down, it's hit the lower side of the filter. And I've got 1200 hertz modulation, but right now the second harmonic of the modulation frequency is only 20 dB down. So I still haven't started rolling off. I'm going to change it to 500 hertz per division. And if I keep decreasing the frequency, now I'm starting to roll off. You'll see the upper sideband roll off the other side of the filter, and I'm at 200 hertz. So there's a couple problems here right now. I'll increase the frequency again. See, this shouldn't be there. That's going to be a problem. What we want it to look like is more like this, where I am at 2K. So I can set my BFO frequency a little further lower, and that will move these frequencies down a little bit more in the filter and may help also. It's 2 kilohertz per division once again. Modulation with 2 kilohertz. Here's the upper sideband. There's the carrier. There's the lower sideband. I changed out the demodulator. The modulator diodes. They were 1N 4148s. I had some Schottky diodes, BAT 47s or 48s. I'm not sure which is still a low voltage Schottky diode. And you see the big difference it made. This is my upper sideband. I have a 2500 hertz modulation signal going in right now. Here's the carrier right down here. So it's 10, 20, 30, 40, 10, 20, 30, 40, 50, 60 dB down. 10, 20, 30, 40, 50, almost 60 dB down. That's a big difference just by changing the diodes. And I can tweak the carrier balance pot, and you can see it come back up. And if I get real careful, I can get it way down there. It's really touchy though. I'll try to get it back to where it was. That's close enough for now. And I'll decrease the modulation frequency now. Well, I did notice it does tend to change the carrier suppression. I'm at 1500 hertz now, but I still have 10, 20, 30, 40 dB of carrier suppression. But this second harmonic of the modulation frequency, that's a 3K signal. That's starting to come back into the bandpass of the filter. So it's starting to come up in amplitude. At this point I can actually take and tweak the modulation carrier balance again. And it goes down. So I'm not sure. I guess probably where I would try to set it is pick something like a middle road like this. And I still have 10, 20, 30, 40 dB of carrier suppression. If I decrease the amplitude of my modulation, the carrier tends to come up. If I overdrive it, the carrier comes up. There's just kind of a happy spot where you get the best carrier suppression. So this carrier, this is lower sideband. What it all should look like would be more like what it does up here around 2500 hertz modulation frequency. All the young water products are about 15, 25, 35, 45, almost 50 dB down. So that's working pretty good there. I just have to get it to where it does the same thing throughout the other modulation range. I'm going to tweak the balance pot there in the carrier. See, and I can really get it way down. 10, 20, 30, 40, 50, about 55 dB down. So maybe I'm gaining and getting closer. Any of you guys that are the experts, please send me an email and give me a hand.